we are pleased to have Professor Ramprakash with us. Professor Ramprakash is senior professor here in IUCAA, and he is also the dean of digital academic programs. His research interests are astronomical instrumentation, and in the instrumentation side, he is involved. We have this middle class telescope, IUCAA Giravali observation, but involved in the setting of that center. Along with that, in Aries, there was this instrument. There one satellite one telescope was installed, 3.6 meter. There was third optical telescope. He was involved with that also. He was involved with one polarimetric telescope in Greece called Robopol. So he is involved in several optical IR instrumentations. And other than instrumentation, his science research interests are polarimetric studies of peeling sequence stars, giant molecular clouds, reverse supernovae. So thank you, Professor Ramprakash, for accepting our invitation. Please enlighten the students with our theory.
So good afternoon, everybody. Oh, that's nice. Most of the time when I say good afternoon, everybody, what is going on? Good. So what I'm trying to talk to you about, the topic which they had mentioned was 30-meter telescope, which is a project which India is part of. It's a multinational program, very big observatory program. But before getting to that, I think my guess is most of you haven't had much exposure to astronomy before. Is that correct? You have an interest, but not have much exposure to astronomy. This must be your first brush with astronomy in the real sense, right? You have seen astronomers in their natural environment. Like you go to a zoo. So I thought I'll give you a little bit of background of why astronomers make this big telescope, big observatory, so that you go with some, not just heard about a project, but at least why it's a project. And I like this to be a dialogue rather than a monologue. So I don't want to just stand here and talk to you for an hour and walk out. So please interrupt me anytime, ask questions. Raise your hands, without raising your hands. If you don't interrupt me, I will interrupt you. You have to answer questions. It is in your interest to ask me questions rather than the other way around. So you have to find answers. So please find questions than making you find answers. Okay, we all like stars to twinkle, right? That's what we see. From very young age, we like to see the twinkling stars in the sky. But astronomers don't like stars to twinkle. Astronomers like stars to stay steady without twinkling, and some associated phenomena related to twinkling. So that's why I said twinkle not with a star. Hey, you don't want stars. That's a nuisance for astronomers. Twinkling of stars. So we'll try to understand why that is so and what its impact for astronomy is, and how astronomers try to overcome that problem. So that will set the preamble, and then I'll move into the 30-meter telescope project and its context, and so on and so forth, and what we are trying to do. So if I ask you that question, what does a telescope do? Not for an astronomer, for anyone. If I look through a telescope,
distant objects.
You can see distant objects, or distant objects appear close. Right? That's what it does. Brings objects close. Right? Now this is, if you want to analyze this, what does it mean by bringing objects closer? There's two aspects. Okay. Basically two aspects. One is it collects more light. Right? If there's a very far away candle, something, a kilometer away, you won't be able to see it. You look through a telescope which is a large diameter, you collect more light, and that candle may become visible. That's one part of bringing an object close. It's as if the candle is closer to you and you're collecting more light at one part. The other part is you start seeing more details. Right? If you are standing a kilometer away, I don't know. I look at you with the telescope, I start seeing the details of the facial features and I know. And so, right? So you start seeing more details with the telescope and you collect more light. These are the two things which astronomers or any telescope does, and astronomers make use of. So more light means object appears brighter, more details means you start seeing finer features of the object. And it's the diameter of the telescope which defines how brighter an object is. Right? If you are looking at something, your eye at the best condition has an opening of few millimeters, 3 millimeters, 5 millimeters, maybe 8 millimeters. The iris of the eye. That's the maximum it will open. So that's the amount of light which can come from that object into your retina. Right? But if you aim that with a telescope which is diameter of this much, and it collects light from that much area and bring it to the eye's opening, that object will appear bright. Right? So that is what the telescope does. The diameter of the telescope makes the object brighter. The focal length of the telescope is what allows you to see finer details. The longer the focal length of the telescope, you're able to see finer details. Okay, so when you want to design a telescope, these are the two parameters you define. Which diameter you need, what focal length. Okay, how much brighter you want the object, how faint an object you want to see, and what fine details. Now, if you compare how much telescopes have come over the centuries, Galileo's telescope, Galileo was the first person to use a telescope to look at the sky and record what he found in the sky. He was not the inventor of telescope, he just used it for the first time in recorded history to look at the celestial object and record what he saw. Galileo's telescope had a diameter of about 40 millimeters. Whereas the largest existing optical telescope has a diameter of about 10 meters. Similarly, the focal length also is substantially orders of magnitude increased from the very first telescope used for celestial observations about 400 years ago to today. Okay. So in both these capabilities, telescopes have come a long, long way. Yeah? So we are advanced over past centuries. Now we are saying that telescope will bring objects closer. Yeah? So first thing you ask is, when you are looking at celestial objects, how far are they? Right? That's a question. I mean, we are bringing objects here, make them appear closer, but how far are they? You have a feel for the scales of the universe? Yeah? Reasonable feel for how big our solar system is, and compared to that, how big our galaxy is, and how big the universe is, and so on. Yeah? Yes, many people are shaking affirmatively, which is good. So, since you have not interrupted me for so long, let me ask you a question. Okay. I take the sun here and put Earth here, put a meter away. Okay. Now I want to put the next star. What is the closest star to our solar system? Proxima Centauri. Any of you? I want to put Proxima Centauri in this model, scale model. The sun is here, Earth is a meter. Where will you put Proxima Centauri? Back to the room, outside in the garden, where will Proxima Centauri go?
Outside.
That's what I meant by we have a scale of this thing.
Outside.
Sorry?
3 points. We consider the distance between sun and.
I can't hear it.
We consider the distance between sun and Earth to
1 meter.
1 meter. Then it will be around 3.7.
3 meters.
From Earth.
3 meters away.
3 point
Something. 3 points something. So Earth is here, sun is here. I want to put Proxima Centauri somewhere, and you are saying 3 meters away. Okay. Okay.
It's nearly like.
Anyone else has a guess? You said many of you said when I saw you have a scale of things. So this is the first scale.
Like light.
Where? Huh?
4 light years.
What?
Light years is the near.
I'm not talking light years. That is in real scale. In the scale model, can you think light years in your head? I'm giving you a physical thing. Sun is here, Earth is here. I want to put Proxima Centauri. Where is that? Sorry? Few kilometers away? Yeah? Proxima Centauri will be in Mumbai. 100 kilometers away. Okay. The sun is here, Earth is here. The nearest star would be about 100 kilometers. Don't quote me on that number. But it's not going to be in the garden outside. It's not going to be where you had your lunch. It's going to be Mumbai. Okay, something like that. So that is the scale compared to a solar system. Yeah?
Sir, in the previous slide that you showed, all those things were valid only for optical telescopes or for
All telescopes. All telescopes. All telescopes do the same. The diameter collects more light, more photons, and focus allows you to see finely. Okay, so for all telescopes. So let's put some scale. Let's try to understand the scale of our system. When we say telescopes bring objects, also what are we talking about? So you know this unit called one astronomical unit? That's the average distance between Sun and Earth. That's what we scale to a meter just now. Right? So that's about 8 minutes it takes light to travel from Sun to Earth. Times 60, so 480 seconds times velocity of light, about 1.5 10 to the 11 meters is one astronomical unit. Right? Yeah? Okay, what is 1 light year? That is about 5 times 10 to the 7 seconds in a year. And the velocity of light, so 10 to the 16 meters. Right? Yeah? So now you see the scale, 1 astronomical unit, and somebody said Proxima Centauri is a few light years away. Right? So there is a scale of 10 to the 5 here. Right? 100 kilometers. Or 10 to the 5 meters is 100 kilometers. Right? For Proxima Centauri is a light year away, that is a few light years away. So around 100 kilometers of the order of distance it has to be away. Right? Is that clear?
Yes, sir.
Yeah? So light year is good. Then astronomers use another term called parsec. How many of you know what a parsec is? It is 1, 2, 3. Some few of you know. Okay, let me quickly explain. Simple. You take a stick like that. You draw 2 lines, converges there, and you put your eye there and measure this angle. Okay. Now, if you put this stick further and further away, this angle reduces. Right? Now, you put the stick so far away that this stick, let us say, is 1 astronomical unit in size. Okay. And it is put so far away that this angle is 1 arc second. You don't know what 1 arc second is. Right? 1 degree is 60 arc minutes, and 1 arc minute is 60. So it's just like time division. So this is a very tiny angle. You know how tiny it is? What is the size of the moon, the sky, or the sun, full moon, or the sun, angular size? Half a degree, right? So this is 1/60th of 1/60th of that, roughly. So very tiny angle. And this is a very large scale on astronomical unit. 1.5 10 to the 11 meters. So this distance has to be really large, isn't it? So I will not work out the details, but you can show that by simple, arithmetic. You can show that it's about 3 into 10 to the 16. 3 and a quarter, 10 to the 16. So it's a few times a light year is a parsec. Okay. So it's also a pretty large unit compared to sun-Earth distance. Yeah. So in this unit, the nearest star is about 4.2 light years away, 1.3 parsec. It's not a light year, a few light years already, right? And it's about a parsec. So typical interstellar distances are of the order of a parsec, a few light years. In the galaxy, if you take stars, typically you say, okay, they have roughly a parsec. Yeah, good. Now, if I take the size of our galaxy, is 20,000 parsecs size, 20 kiloparsecs. Compared to typical interstellar distances, is 20,000 times larger. And this interstellar distance itself is 10 to the 5 times order larger than Sun-Earth distance. Sun-Earth distance itself is a large thing. 8 minutes light takes to cross that distance. Right? So this is a huge size. And then if you take the nearest galaxies, the Milky Way has some dwarf galaxies around them. What are they called? Magellanic clouds. Right? Have you heard of them? They are about 50 kiloparsecs, roughly. Okay, they're pretty close. If I take the nearest galaxy to our galaxy, Andromeda, it's about a megaparsec, another factor of 1,000. Okay. Yeah. So if I take, so typical intergalactic distances are about a megaparsec. So typical stellar distances are kiloparsec. Galaxies could be of several thousand kiloparsecs, tens of thousands of kiloparsec size. Intergalactic distances are another factor of 1,000 megaparsec. Yeah. Similarly, what is the size of the observable universe today? What is the largest scale you can think of? How big is our universe? I'm not asking about the physical size, I'm asking how far can you see? But do you have an argument of how far you can see? So universe has an age. What is the age of the universe? Huh? Some 14 billion years. How far light has traveled in that time, so that far you can see. Right? So that turns out to be a gigaparsec, 2 gigaparsec, another factor of 1,000. You know that, that's right. You understand? So each scale is a factor of 1,000 we are talking about. Yeah? And when your starting point, the locus run itself of the ladder is a huge distance already. In this context, what does it mean that they are infinite? Right? Even if you make a telescope as large as that, whole Earth is a telescope. Compared to that, these distances are infinite, isn't it? So what does it mean by bringing object infinity closer? What does it mean? We all agree telescopes bring objects closer. That's why astronomers use them. This context, what does it mean?
The light emitted from them should be focused to
Light?
the light emitted by the radiation emitted by them should be focused by the telescope. So
Yeah, that is correct. That is how it makes it brighter. That is one element of how objects are appeared to be brought closer. Right? One is it makes it brighter. The other one is you are able to see the finer features. Right? But in that context, these objects are in. Let me come to that. So you're just leading me to my next slide. Okay, good. So I put a star there. Light from that star is radiating away. That's what you're saying. That's what you said. Right? Light coming out of this star is radiating away in all directions. Yeah? Now if I put a point star in that sky out there, it's a point, it's a dot. Right? And it is emitting light in all directions. Now what does it mean by bigger telescope collecting more light from it? How does it happen? It's just a point in the sky, anyway. Isn't it? Just a point. So how does it matter my telescope is this big, this big, this big, or my eye? How does it matter? Just a dot in the sky. That's what I'm trying to explain here. So the light from that star will radiate in all directions. Yeah. So you think of this light radiating away and expanding away as a sphere. But we just learned that these distances are enormous. So by the time the light gets to somewhere where we are sitting, this curvature is almost zero. Right? It's a sphere of infinite radius. So these rays which started coming out radially, divergingly out of the star, appear to be arriving at this parallel. If you have a spot in the sky, you are not seeing rays coming like that. You are seeing rays coming parallel to my line of sight to that spot. All the rays are arriving like that. You understand? Because it's a part of that big sphere, infinitely large sphere. Yeah? So if I put a telescope there, depending on the diameter of the telescope, I am going to collect more and more light. Although it is a spot in the sky, understand? And the amount of light you are going to collect is just directly proportional to what area of the sphere you are going to sample with your telescope. The area is 8 millimeters of your eye. That is the part of the light you are going to collect from that star. If you have a 40 millimeter diameter telescope like Galileo, you're collecting light from 40 millimeter area and focusing it with your detector, whatever. Right? Or if you have 10 meter diameter Keck telescope, you're collecting a bigger sample. That's all. And that's how the object becomes brighter. Yeah? Is that clear? Yeah? Okay, good. So, good. We just demonstrated that taking a bigger telescope allows us to see fainter objects, right? Because it collects more light. And if your eye, how many light particles, photons should reach your eye to start seeing something? Now, there's a certain number of signals should be there, right? Typically, if you are looking at something with your eye, what is your typical number? Any ideas? If you collect about a couple of hundred photons per second through your eye, your retina is in a signal. Okay. So if a star is provided too faint, and the sphere is enlarged over that infinite distance, and the light, fraction of the light in an 8 millimeter area is less than 200 photons per second, you won't see it. It's too weak a signal. But if you put a telescope in front of it and collect from a larger area and put it into your retina, of course you will collect more than 200 photons per second, you will start seeing it. So you will see fainter objects. Is that clear? Good. So, next question is how faint can we see? That naturally leads to thing. Okay, I keep making my telescope bigger and bigger. Can I see arbitrarily fainter and fainter? Is that possible? You bigger your telescope, you fainter and fainter it comes you. Is that possible? Yes or no? Is there an upper limit or a fainter limit?
There's a limit.
Sorry? There is a limit. What is the limit? Sky is not the limit. Huh? What is the limit? How faint can you see? Natural. If I go out now and look at the sky, do you see any stars? Why?
Because light.
Huh? The sky is so bright, you don't see it. Is the sky the limit? So you go to some night sky, look at it. Night sky also has some glow. Right? Especially in a place like Pune, all the city lights is thrown up in the sky, not where we need the light. Right? All the fancy lights are up, going in the sky, scattering in the atmosphere and coming back. The sky appears so bright, you have no stars. You don't see anything. So much night sky light pollution. It's not air pollution, water pollution, light pollution. Right? The cities. Stars are on there. No stars. So you go to a very remote place where there is no city and look up the sky. Even that night sky has some brightness. Some photon is produced. Is that the limit? Can you see anything fainter than that? Yes or no? Come on. You are not asking questions, I have to ask you questions. So can you see anything fainter than the sky? Whatever, however faint the sky is, it's still producing some light. Right? Some emission should be coming. All the scattered light from the stars or dust scattered light, whatever it is, does not matter. Something light is coming from to us in the sky. Could be just coming from our atmosphere, like light pollution. Even that contaminates. It appears like coming from the sky. Right? So anything. Is that limit? Can we see object fainter than the sky? Yes or no? If you can't, then there's no point making bigger and bigger telescope, right? If they make a telescope big enough to see as faint as the sky allows, end of story. Right? Sorry? Sorry?
We should use some technique to cancel the effects of
No. You're expecting 5 slides ahead. So that we'll come to that later. Let's address this now. Yeah? So I'm just trying to say simple, let's forget even atmosphere for now. You're looking at the sky, there's no atmosphere. Let's say for now. And the sky has certain brightness. Can you see anything fainter than that? Yes or no? I need an answer, otherwise I'm walking off.
Yes.
You have to commit. The light earlier you said the nearest star is like kilometers away. It's okay, we worked it out. We figured it out that it's not that close. Right? Let's have some answers.
Yes, we can see that.
Yeah?
Naked.
Can we see anything fainter than the sky?
Yes.
No?
Yes.
Okay, good. So you are saying you cannot see anything fainter than the sky, so I have drawn a patch of sky here. Okay, dark sky. I put a star there. It's a pretty bright star. Right? Now I'm going to make that star fainter. Fainter. PowerPoint allows you to do all kinds of magic. It takes a lot of time, but it is. And I make that star fainter. Become fainter than the sky, you don't see it. You see the star there? I didn't take it out. I make the sky a little darker. Okay. Star is still there. I'm not cheating. Right? In this image, you don't see it because this patch is brighter than the spot there. Now, if I make this patch darker, star is still there. You now see it. Okay. So somebody said you cannot see something fainter than the sky. Yeah? Is that correct or not? You agree?
Yes.
You all agree? Then we'll move on. Yes? Okay. So astronomers don't give up so easily, right? And you also should not give up so easily. Right? If you say, okay, sky is the limit. Okay. You don't do that. Move on. You have to beat it. So I'm giving you a technique. I'm looking at this direction of the sky, and then I am measuring the total light coming from there. I look at this part of the sky and total light coming from there. Subtract one from the other. One place is excess light. You say, okay, there's something there. Technology allows you to. Right? Yeah? And then go on. Yeah? Your question?
It's doing the same thing. It's the same amount of light coming from both parts.
Yeah, I mean, you keep on searching. Right? Wherever you see excess light, relative to adjacent area, you know something is there. And that excess light is coming from some object. You can measure it. There's no, at least in principle, there's no problem. So I'm contradicting the theory that sky sets the limit by saying, why don't you do this? A simple thing of sky subtraction. Right? Yeah? Yeah.
How can we be so sure about the fact that this light, the background light is that is, there may be some random factors in that.
Yeah.
But then I think subtraction is not
Yeah, you are anticipating 3 lamps in this time to get there. Okay. But I know if you know exactly how to quantify it, good, keep quiet. But I want to make that quantifiable. Okay. We are driving. Okay, so this argument is, okay, this is what I asked, what to put the subtract in the sky. Right? Take this sky here, total light from here, total light from here, subtract one from the other, you should see any excess, there should be some object there. Now he is saying the sky may not be constant. That's what you're saying. But how well have you measured the sky? That's a question. Right? It may not be that the sky is changing. It is something more fundamental than that. That's what I want to try. Let us assume for the time being that there is no funny thing going on in the sky. It's a steady sky. Nothing is changing. Not like sun is setting and the brightness is changing. Nothing like that is happening. Okay, everything is constant. Identity. Even then, if I want to measure how much light is coming from that part of the sky, it has a fundamental limit. Okay. This is nothing to do with the technology. This is nothing to do with what detector you use or how you measure the properties, anything. It is the way photons behave. Okay, it's physics. Comes from the physics. I don't have time to explain why it comes out of physics. But take my word, if I collect in an experiment 10 photons, okay, from something, any object, you know that n only to an accuracy of plus minus root n. What I mean is, if I do this experiment multiple times, each time I collect on an average n photons. Each experiment will have a variation where standard deviation is root n. Is that clear? This is the nature of photons. Either you can derive this thing by thinking of the statistical process of emission of light. Right? You think of a star emitting light, and I'm collecting light from that star with a camera which has a 1 second exposure time. Okay, I open the camera for 1 second, collect photons, and close it. Every 1 second, there is no reason why the star is producing exactly the same number of photons. Right? What is the process of producing photons in the star? Some fusion happening in the core, photons traveling through that atmosphere of the material of the star, coming through that atmosphere. It's all statistical. Right? So every time you measure with a 1 second exposure light from the star, you will not get the same number naturally. Isn't it? The star is not producing it's not because the star is changing. You make multiple measurements, large number of measurements, the average value will stay the same. It's not the star's light is oscillating up and down. It's just that every experimental measurement, you're not getting the same photons. That is all. Right? And take an average, you get the same number again and again. Yeah? So the uncertainty is root n. You can't beat it. No way to beat it. We haven't found physics good enough to beat that limit. Okay. So if I collect some photons from there and photons, I know that number only with an uncertainty of root n. Similarly, the total light that I collect from there also I know only from uncertainty of root n. Yeah? Now, with given this, let's go back to this question. Can we see object failure than sky? Okay. So let me make a table. Yeah. This is the number of photons which I collect from the star. How much photons the star only emits. This is the number of photons the sky adjacent to it emits. Yeah. This is the noise in the star measurement, which is just the square root of this number. And this is the uncertainty in the sky measurement, which is the square root of this number. And I create a quantity called signal to noise ratio. What is signal here? The number of photons I collect from the star. What is the total noise? This total. Right? That's the uncertainty in this measurement, uncertainty in this measurement. Total of that. It's just that one detail is that this uncertainty don't add up like that. They add in quadrature. You square them, add and take the square. It's a minor detail. Let's forget that detail. But that's not material to all the calculation. Understand? Yeah? That is reason. The reason is when this starlight, maybe in that measurement, the starlight is higher, the measurement of skylight is below average. The other experiment, this may go other way around. So just adding the uncertainties will overestimate your number. You add them in quadrature and take the square root so that the sign doesn't happen. And noise addition. Is that clear? Yeah? Anyway, that's a D. So I am looking at this situation where the star is producing 1 photon per second. Let me take out the telescope. The sky is 100 times brighter. Right? So the noise from this measurement is 1. Square root of 1 is 1. Noise from this measurement is 10. Right? So you plug in this expression for signal to noise ratio. Signal is 1 divided by root of 1 squared plus 10 squared. This is like that. Right? 1 is not adding anything. Right? It's 10. So signal to noise ratio is 1 by 10. Your signal is 10 times weaker than the noise or error in your measurement, uncertainty in your measurement. You are not going to see that stuff. Right? Is that clear? What I am saying is, if I make a measurement of the sky here, it has an uncertainty of 100 plus minus 10. And if the star is producing only 1 photon, 100 plus minus 10 is increased by 1 or not, I don't know. This is all in my noise of measurement. Uncertainty is my measurement. That is what I am capturing. Right? Effective. Is that clear? Yeah? Sky has a measurement uncertainty of 10. 100 plus minus 10. So in this direction, whether I get 1 excess of count or not, I can't see. No. My confidence level is very bad. My measurement. Yeah? Now if I make a telescope which is collecting 100 times more photons. So the star I get 100 photons. Sky also becomes 100 times brighter. Right? Now this error is 10. This error is 100. The signal noise ratio is 1. Okay? Signal is 100. Noise is square of this plus square of this, which is like 100. So this is negligible mistake. Right? Square of this square root is just 100. So 100 over 100 is 1. You're barely being able to see your measurement uncertainty is barely equal to your signal. Maybe, yeah, maybe. Right? Make that telescope even 100 times bigger. Right? So you are taking 100 times more light from star, 100 times more light from sky also. But uncertainty, this is 100, this is 1000. Now if I take the signal to noise ratio, 10,000 divided by 1000. This is 10. Signal is 10 times brighter than my noise. You see that stuff. You can measure that stuff. Right? So that's why astronomers make bigger and bigger telescopes. Because although the sky sets some limit, God has given a little handle, little room, where the noise goes like a root n, not like n. That would have been difficult. N squared would have been even more difficult. Right? It goes only, the uncertainty goes like root n, which means you can use that to beat the sky. Yeah, and get to failure and failure measure. It doesn't matter. And you have more money, make bigger telescope, more accurate instruments, measure the light more accurately, collect enough photons, you go as faint as you want. Yeah? So the light, the sky background is not really the limit. It sets a limit in how accurately you can do the measurement. By collecting more and more photons, you can get fainter and fainter. Yeah? Clear? So that is the motivation for astronomers to make bigger and bigger telescopes.
So does that mean that if we make huge telescopes, then we have not be able to detect more fainter stuff?
Yeah. Go on. Depends how rich are you? What is the salary? How rich are you? You're not rich? The bigger the telescope, the cost of telescope building goes something like the cube of the diameter. Okay. So a 10-meter telescope here, this telescope is a Keck telescope, which I mentioned in my first slide, on top of this beautiful mountain or Mauna Kea. Okay. So you can see the clouds below the mountain. This is so high, 4,200 meters, almost half the height of Everest. Right? All the observatories, big observatories are up there. So that is one reason why you should become an astronomer. Go to all these beautiful places. Right? Yeah? If you like traveling, come to astronomy. And so this is a Keck telescope, 10-meter diameter. You want to get one night or operational cost of one night of the telescope. Guess how much? Crore. I'll give you a crore. Give me one. I'll give you a crore. Give me one. It'll be something like $150,000 per night. Okay. It's like a crore. So, so that is one night operational cost of that. Okay. So if you have enough money, you can make bigger and bigger. But it's become very expensive, very quickly operate. And the 30-meter telescope project, which I will be, if I have time and we get to, that we're talking about, is going to cost $5 billion to build. And we have been working on that project. Okay, that we'll get later. Okay, that's the 10. You can see the primary mirror of the telescope, 10 meters in diameter. Right. There are two of these on top of Mauna Kea. You can see this is these are some trucks parked there. These are just that height is height of a story, one-story building. So this is a huge facility, very complex facility, built on a mountain, half the height of Mount Everest, in the middle of Pacific Ocean, right in the middle of Pacific Hawaiian Islands. So human beings make a lot of effort to build this facility. They are not small and challenging. Anyway, so we'll skip through. These are some other telescopes. This is a 200 inch, or 5-meter diameter Palomar telescope, blah, blah, blah. So let me run out of time. So this in southern hemisphere, again, in the Chilean Andes mountain, there are these 4 8-meter diameter telescopes, etc. So this is a collage of all the large mirrors. These are 4 meters in diameter. These are like 8 meters in diameter. These are like 10 meters in diameter. The blue ones are in the northern hemisphere. So yellowish ones are in the southern hemisphere. So astronomers have made a lot of big facilities around the world. Now the world is moving to the next generation. So the largest existing ones are 10 meters in diameter. So this one, called the giant Magellan telescope, the diameter is about 25 meters. So nobody can make a mirror of 25 meters in diameter, single mirror. So these are made of 7 8-meter diameter mirrors, joined together to form one surface. Okay. Then there is this 30-meter telescope, which has about 500 hexagon-shaped mirrors packed together to form one surface, which is 30 meters in diameter. Okay. And India is part of building this facility. And this is a European extremely large telescope, which is about 39 meters, going to the southern hemisphere. And this is made of about 1,000 hexagonal segments packed together. So you can't even see the segments so packed together, but they are made of about 1,000 segments. Okay, so compared to the largest existing telescope, which has a diameter this big, the European extremely large telescope, 39 meter, will have a collecting area that big. You can fit almost all the other telescopes in there. Collecting area. The net collecting area of the next generation telescope is going to be so large that it is bigger than the total collecting area of all the existing big telescopes. So anyway, so that's going to be a big jump. Now, I don't know, I have 15 minutes now. I want to decide how to go. Maybe I'll spend a couple of minutes. Do you recognize this diagram? What is this? Yeah? What is it? Star trails, but why is it looking circles like? What is peculiar about this? Yeah, so the center of this, so if you look at the stars in the sky, they all appear to follow the circular trails in the sky, right? Why is that? We are sitting on the Earth and Earth, we are rotating, sitting on the Earth around the Earth's axis. The axis of the Earth is pointing to the polar axis. Right. So if I think of the axis of the Earth is like this, yeah, then I'm sitting on some latitude here on the side of the Earth. As the Earth rotates about the axis is going to rotate a circle here. The sky. That's the trail of the star. Right? Yeah? So those are those trails. You're just seeing it in reverse. That is all. You are rotating, but we see the stars. How fast are these trails moving? 24 hours for 360 degrees. Which means about every second is rotating by 15 arc seconds. And every hour 15 degrees, or every minute 15 arc minutes, every second 15 arc seconds. The sky is still rotating. That's the speed at which the sky is rotating. And this is just a time lapse movie showing that. Right? The star trends. Okay, so the telescope, if I want to look at a star, and if I said the error in your measurement is square root of what? Square root of what? Number of photons collected. So if you want to collect a large number of photons from the star, I have to keep staring at the star and keep collecting photons. You have to take long exposures. Right? By the time the exposure is taken, the star is going to, which means your telescope has to track the movement of the object in the sky, take long exposures. So these big facilities will have to move in multiple axes to keep tracking of the objects as they move across the sky, so that you are able to take long exposures and thereby collect enough number of photons to keep your noise low. Yeah? Okay. So I will not go into the details of it, except to say that when this tracking happens, there are many factors which affects the tracking. For example, this facility this is the 8-meter diameter telescope. So this size is about 16 meters. Okay. You can see 8-meter diameter mirror. And this is moving around. So it's a optomechanical challenge to keep the optics aligned. Right? When it moves like this, micron level misalignment with the optics, your image is gone. Yeah? So it's a big challenge. In addition to that, there is atmospheric effect, which is one of the effects is called C, which is what leads to twinkling. Okay, so let me come to that and how we overcome that. So before that, if I take a, because you are not asking questions, you are just sitting there and shaking your head. So I have to find out what is this? Do you have any questions at this point? Ask. Everything is clear? Yeah? Everything is clear? Huh?
I have a question.
Yeah.
How do you decide the location for the telescope?
How do you define the?
Decide the result of
Oh, that's a big challenge. Let me try to come to that maybe with this. There's a lot of considerations going to deciding the location. We generally find out the most beautiful place on earth and go there. That's the basic thing. But more definite answers are. Okay. So if I take a centimeter by centimeter box here, fictitious box, how many particles are in it? Okay. 10 standard, 12 standard, some point you are all 6 standard? Something figure it out. 1 cc of atmosphere is standard temperature. How many particles? You had some relation. Yeah? Heard of burger called Avogadro?
Yes.
Yeah? Yeah? So what is Avogadro? What did Avogadro figure out?
Number of molecules present.
any gas for
22.4 liters contained Avogadro number for Avogadro. Right? 10 to the 23.
Yes.
22.4 liters STP, standard temperature contains Avogadro number of particles. So 1 cc is 22.4 scale by 1 centimeter. liter to centimeter cube, then 22.4. So you will find that there is about 10 to the 19 particles in a 6. Okay. If you make the best vacuum, the technology can get you. Okay. How many particles were in that CC? Yeah. How do you quantify how good your vacuum is? By pressure. You say, okay, there's so much pressure. Atmospheric pressure is how much?
1 atm.
1?
1 atm.
1 bar. Everybody remembers bar. And 1 bar. So, okay, some unit. So, what is the best vacuum people have created? Yeah? Compared to that, what is the pressure in the best vacuum? Okay, it's of the order of 10 to the minus 6 millibars. Okay, 10 to the minus 9 bars. Okay, so 10 to the minus 9 bars means that thing still contains about 10 to the 10 particles in a 6. That volume. Right? PV is and kT. Given temperature, pressure goes something, volume stays like that. Right? Volume or density, P is equal to N by V kT. Right? So that still contains, 1 cc still contains about, so the best vacuum people have created still contains about a million, tens of million, 100 billion particles. This is, okay, so it's not vacuum, it still contains so many particles. But if you go into space, a cc of space may contain only hardly a particle. It may take 10 cc volume to kind of find the particle. That's why it's called space, really space. Right? Still not empty, still contains particles, but the density is so low compared to anything you know. Now, when you think of this light which is traveling from this infinitely faraway stars, it is passing through this kind of medium. And then it hits the atmosphere, boom, into the 19 cc per cc. Right? It's so dense compared to anything in the space. The light has passed over its billions of years of travel, millions of years of travel through the atmosphere, through the galactic medium, and the stellar medium, the density is so low, it hits the atmosphere. So, the atmosphere is a very, very dense medium compared to anything the light faces. And the atmosphere is not very uniform, homogeneous medium. It's always in turbulence. Right? Heated, cold, sun heating, human activities, all kinds of things. Atmosphere is not a very nice medium. Right? It's a very bad medium. So when light passes through the atmosphere, of course it is affected. Right? So, for example, if I take one line of sight through this atmosphere and another line of sight, the total path length, integrate n dt, right? N is the refractive index, integrate it over the path. There is no reason why the two integrated refractive index along these two paths are exactly the same. The density, temperature, etc. along this path would be very different. And this could be changing over time. In fact, it's changing over millisecond time scales. The two things which are separated by this distance, the total integrated path length through these two different paths are changing at millisecond. Every millisecond, this path difference is changed. You understand? So, what is the effect of this? You remember that nice plane wavefront which reached above the atmosphere, where the rays are on parallel. Now, if I send a ray here and send another ray here, which is the path length is changing, the rays tend to tilt around. And also there will be phase difference. Isn't it? By the time the ray which is starting together from the top of the atmosphere, by the time this ray reaches the ground, this ray might have reached to this part. This part is, n dt is different. This part compared to this part. Yeah? And of course, if refractive index changes in the medium, rays bend. Right? So all that affects light passing through our atmosphere, and therefore these plane wavefronts which are coming through the atmosphere gets distorted as they pass through the atmosphere. Okay. And what is happening is this distortion is not steady. Every few milliseconds, there's a completely different distortion shift of the wavefront. Yeah. So what light really falling on the telescope is like this. The wavefront is like that, not the nice plain wavefront they showed several slides away. Okay, that clear? So this has an important effect. Instead of a nice image of a star, the telescope focal plane, when I take a time-lapse movie, a very short exposure with a very large telescope, very short exposure, 1 millisecond, 1 millisecond, 1 millisecond exposure, and we'll create a time-lapse movie. The image looks like this. Because this atmosphere has distorted this wavefront. Okay. So, ideally speaking, that image of the star should have been, the tiniest spot of blob of light in here, not this big blob, the smallest structure. The image should have been that big. Instead of that, the light has been spread out over area and the whole thing is jumping around. So if I take a 1 second exposure, in that time this light would have jumped around all over the place that it would fill this area in a Gaussian. Many of these patterns will fill that area and the overall light pattern will be a big blob which is Gaussian distributed. So many random things added up eventually until a big Gaussian. Okay. Yeah. So the image of the star is not going to be a nice spot on your telescope focal plane. It's just spread over the big area. Okay. So this is a big limitation. I'll stick to all this because I have to get the TMT. So the big limitation is, ideally speaking, if I send a coherent beam of light through an aperture, which is the telescope mirror, at the focal plane of the telescope, I should get this airy disk pattern. Have you heard of this airy disk pattern? Refraction pattern of the circular aperture. Take a circular aperture, illuminate with the parallel beam of light, put a screen far away, you should get that diffraction pattern. Right? That should be the shape of the image of a point star in the sky. Right? And the angular size of that would be lambda by d, Rayleigh size. Right? Those who would have paid attention to this in optics would know Rayleigh criterion. But the atmosphere, because of the distortion of the wavefront, and this is true if the wavefront was plain parallel and coherent and passing through a circular aperture, passing pattern would look like this. So at half micron wavelength, which is a typically visible wavelength, looking through a telescope of 10 meters in diameter, this diffraction limit should be 0.01 arc second, tiny. The point will really appear like a tiny spot on a telescope. 0.01 arc second is very tiny angle. So here I said the object has an angular size of 0.01 arc second on the telescope. Yeah? That's nice. That's what you should expect. But the atmosphere, make it spread over 0.5 arcs or even bigger, 1 arc. That distortion. Is that clear? So what it means is that while the telescope should have been able to see fine features as fine as 0.01 arc second with 10 meter telescope, atmosphere spreads the light over an area which is bigger, 5 times bigger than this, is 0.1 arc second diameter in this scale. The actual spread is 0.5 arc second. You can't fit that in the screen. Understand? 5 times this area or 10 times this area. That much area is spread out the light. The effect is all those fine features the telescope should have been able to see is all washed. Right? Each point, you can think of a galaxy as the spread of point sources. So each point source, light is spread like this area. You're not going to see all the details. Right? So that's the limitation of the atmosphere. And of course, like what I said before, astronomers don't give up. We find solutions to this. I don't have time to explain that. And the solution is called adaptive optics. And using adaptive optics to an image of the star. This is a real image taken as a movie. The star, which is, the star light is changing. So the atmosphere spreads it around. Now I am turning on adaptive optics in a second. Come on. Stop. That diffraction pattern. All the light is collapsed, and that noise diffraction pattern comes. So you in real time measure the distortions introduced by the atmosphere using lasers, and then do some magic, compensate for it, so that you get the diffraction limits performance of the telescope. That's what is called adaptive. So all modern telescopes will have this adaptive optics system. You can see the Keck telescopes here, two of them, sending laser beams into the sky to measure the way atmosphere is distorting the wavefront. Because these lasers are creating artificial stars high up in the sky. From that artificial star, the light coming back will be measured. And using that measurement, it compensates for the atmospheric effect and get the diffraction limit performance. This is just a couple of movies to illustrate. So without adaptive optics, with adaptive optics. See that? So all that fine features, nothing. There's big blobs of light, right? Adaptive optics start working. You see so many beautiful stars out there. Similarly, Jupiter, this is what you see without the planet. Moon, all that. Anyway, so if you are looking towards the center of the galaxy, this is actually an extrasolar planet. You look at another star and see if there are planets around the star. If the light from the star was spread over this big an area, you haven't got to see any of these planets. With adaptive optics, you collapse the light into the diffraction limit, then you can see nicely planets moving around the star. Extrasolar planets. Yeah? Okay, good. So, let me come to the real topic. Shall I take some? Yeah, you tell me you're bored. Finish? At any time we'll go, right? So we can stop anytime. Okay, or you say you have been saturated.
Snacks will be at 5:30. Snacks will be at 5:30.
5:30. Okay. That's a real upper limit. Okay. So there is this project called 30-meter telescope, one of the telescopes which, the reason why I explained all this, I could have just jumped into this slide and said we are doing it. And you go away, okay, why are we doing such a thing? What is the purpose? How does it help? Right? So I wanted to build that context. Why astronomers make bigger and bigger telescopes, put it in some quantitative footing. And also, what other essential, just building the telescope is not good enough because you are going to look at the atmosphere. Now we know why we go to a 4,200 meter high mountain. Because at that height, only 60% of the atmosphere is above. Okay. So you reduce the amount of atmosphere, it helps at work better. Yeah. So one of the things to choose is to go to a place which is very quiet. Because the wind blowing is very laminar, not turbulent. For example, in the middle of Pacific Ocean, nothing to disturb the wind flow for thousands of miles. There's suddenly a big mountain there, top of the mountain, above the clouds, no light pollution. Right? Rain will all be below. So that one fine place where instead of looking up at cloud, you down above the clouds. Okay? And there's less atmosphere. So those are the typical considerations to make choose a location. Okay, and of course, rain. If there are more details, like less dust content, less water vapor content, there are more details, but these are the main. Okay, so India is part of this project called 30-meter telescope. As I indicated in one of the slides, the world is now jumping to the next generation telescope, building the next generation bigger facilities. Because this technology driven. You make a 10-meter class telescope, Keck telescope, they were built in the 90s. They became operational in the 90s. And technology has not progressed so far to conceive building a bigger 25, 30 meter telescope. Even now we are struggling technologically to get all the things matched up, work together. Because the reason is, as the telescope becomes larger, the lambda by d, you are aiming at more and more finer. Lambda is fixed, half a micron, 1 micron, light wavelength. D given is 10, you saw that angular resolution is 0.01 arcsecond. But now D becomes 30, you are driving to get angular resolution which are much finer, which means the mirrors have to be aligned much better. This has to form one surface. When it's tracking, they all have to stay together. So everything becomes challenging. And that fact. So that is why technology has not reached. Even 30 meter is at the edge of technology to achieve. That's the best we can conceive to build at this point. 30 to 40 meters. Anyway, so these are very complex facilities, difficult to build. I will not get into the details of it. All I wanted to say is we started this whole program in 2007. What year is now?
2023.
2023. So how many years? 2007 to 2023. Huh? Arithmetic. I can say that loudly. Okay. We haven't even started building this facility. Okay. We've been working more than almost 2 decades now. We haven't just started building the facility. That complex because we don't yet have the technology. So that's one reason. Anyway, where is it going to come? Again, it's going to come in Hawaii. Hawaiian island in the middle of the Pacific Ocean. Mauna Kea, the same mountain. India, Canada, China, Japan, Canada, and America. These are the partners. All these countries are joining together to build this facility in Hawaii. As I said, it's about $5 billion to build it. We hope to start construction in 2025. I'll come to start there, okay? Anyway, these are the reasons why we go to these sites. The seeing, I said, the fingering or spreading of the light is very good there. The light only becomes 0.4 arcsecond 25% of the time. No? 30 meter diameter telescope should deliver an image which is 0.003, 10 milliarcsecond or better. Compared to that, this place will deliver 400 milliarcsecond. That has to be corrected by adapter to get to the diffraction. So that is one reason. But if this 0.4 was 2 arcsecond, it would have been impossible. Okay. And similarly, so this is a photo of the actual mountain top. This is where the TMT is going to come. And to put things to scale, this is an artistic impression. That's Kutubina. That's gateway. So that is the scale of things, 18-story high building to be built up on top of volcanic mountain, half the height of Mount Everest. That's a challenge. Okay. So the mirror is made of 492 elements, hexagonal elements, joined together to form a primary mirror. So light comes from the top. This mirror will focus it to the secondary mirror here, and then come back again onto the tertiary mirror here, third mirror. And this mirror can rotate and then divert the telescope beam to instruments, which do various kinds of analysis, spectroscopy, camera, polarimetry, various kinds of analysis of the light to study the nature of the light coming from those objects. So that's our configuration. This is a photo of the largest existing mirror in India, which I mentioned about 3.6 meter diameter telescope, yeah, which is the largest in India at the moment. And that will nicely fit as a tertiary mirror of the telescope. That's the scale at which we are talking. Jump. So the largest existing mirror is not even as large as the tertiary mirror. So that tertiary mirror is as good as a big telescope. It's going on its own for this facility. You understand? That's the kind of stage we are going. So, anyway, we'll have adaptive optics system. Otherwise, purpose is defeated, right? You make this big telescope, atmosphere tells you how fine lenses you can get. End of story. Okay, what does India, how is India going to participate? There are 3 institutions in India. One is ADIS in Nainital, the Institute of Astrophysics in Bangalore, and IUCAA. These are the 3 PI institutes. We are the Indian PIs of the institute. It's an India TMT coordination center at the Indian Institute of Astrophysics in Bangalore, which is really coordinating all the activities, etc., etc. I will not get into detail. This whole project in India is funded by DST and DST as a joint program under the mega facilities for basic science. Indian contribution itself is about 1,200 crores. That's our part of the overall project. And many institutions, etc. participate. So as I said, 2007 we started. 2014, the Prime Minister announced we are joining this project finally. And 2015 onwards, we have been building various components of the telescope. I will tell you a little bit more. We hope to start construction of the telescope on top of the mountain in 2025, and we finish construction in 2037. This is a telescope for you all. I'll be gone by then. Hey, long gone by then. At best, I'll be walking like this, right? By then. So it's all facility for you being built. And let me put this in context. I told you $150,000 for the existing charges spent with the Keck telescope. So if I make a proposal to the Keck telescope and I say I want to use the telescope for some observation, let us say you get 2 nights. Those 2 nights are worth a PhD. Okay. Because by the time your science case is built up, you have done enough background understanding, study of that topic. To get time on the Keck telescope, even 2 nights, you have done enough for a case by that. Right. For a telescope of this class, if we get half an hour on it, it's worth it. You have to do that much proprietary work. It's so competitive. You have 3 such facilities, and people are trying to get time on it. And the best proposals get time. You have to make your best proposal that good. You have done enough hard work. So start now. This is going to come in 2037. Start now. Prepare for it. A long way to go. Okay. That's the message. Start now doing good astronomy. By the time this facility comes, you might start getting back on. Okay. There is no hope. Okay. So in 2037, we will finish construction and then another 50 years of operation. 2085. And then you all will become 2085. Your kids will be doing the science. Okay, what are we doing? We are paying 30% of our total contribution in cash. As the telescope has to be built in Mauna Kea. The road has to be constructed in Mauna Kea, the bulb has to be, electricity for the bulb has to be paid in Hawaii, not paid here. Right? 30% of the cash is common. But 70% of our contribution is for building components of the telescope. In the next slide, I will tell you what we are doing. It encompasses everything. This. And that is true for all partners. Okay. So different partners are building different components of the telescope in their countries. So if I take one mirror, I told you this telescope is made of, mirror is made of about 500 segments. If I take one such segment, which is this gray thing, there are these things called X sensors there, about 3,000 X sensors, which make sure that the mirror segments are aligned at any slight deviation, nanometers. We are talking about 20 nanometers of deviation. Okay, of these 500 segments. At 20 nanometer level, you have to sense them and align them so that it becomes a nice hyperbolic surface. And this is not sitting in a lab and blow down. It's sitting on that mountain. Winds blow. All kinds of disturbance. Even the ground shaking. It's a volcano. right? Under those conditions, these 500 segments have to be held together with 20 nanometer precision as a single surface. Okay, while the telescope is moving around and tracking objects in the sky. Yeah, that's a technological challenge. So these edge sensors sense those differential motion with the mirrors, produce those signals. All those edge sensors are being built in India. Okay, they are building them. These are these actuators which, based on these edge sensors, can correct the positions of the mirrors. Those actuators are being built. Yeah, positioning system. This entire complicated optomechanical assembly, which will make the primary mirror, the telescope, float as there is no gravity. Because if there is gravity is felt, the shape of the mirror changes. When it is looking like this, telescope mirror is looking like this or looking like this, gravity is felt, the mirror shape changes. So it has to support the mirror cell by compensating, almost negating the gravity. That entire structure is being built in India. Even out of this 500 mirror segments, about 90 of those segments, about 100 of those mirror segments are being built in. Yeah. So the heart of the telescope, the primary mirror, and what holds together the primary mirror as a primary mirror. So, made of 500 pieces to 20 nanometer precision in real time. Right? That's all been made in India. So it's a serious contribution. It's not a peripheral contribution. So that's the overall size. You can see a human being standing there. Within 30 meters, it's like a small football field. So anyway, I'll skip to these details. These are all being built in India. Now, what will it deliver? This image captures the finest image of the sky human beings have created so far. It's called the Hubble Deep Space. You know Hubble telescope? You almost have heard of Hubble telescope. So you point Hubble Space Telescope into some part of the sky and take a very long exposure. This is what it's. It's called the Hubble Deep. So Hubble, being above the atmosphere, doesn't have all the distorting effects of that. That's why people put telescopes above the sky, above the atmosphere, and in space. Yeah. So this is among the finest images. Okay. If I zoom into one of these galaxies in the Hubble Deep Field, it looks like this. Okay. Now with TMT, if I look at it, it looks like this. Of course, the simulation. That's the best you have now. With the best telescope in space, that's what TMT is for that also. You now can study all these tiny star forming regions, all the structures and the bulbs, maybe a bar, all kinds of details. So it's arms going around, dust lanes, all the beautiful details. It's all washed out even with the arm. Yeah? Okay, so the TMT will address some of the real fine questions in sky. Now, let's skip through this. One of the things which TMT is going to look for is to characterize the atmospheres of extrasolar planets and see if we can find any evidence for life. Things like methane or ammonia, that kind of thing in the atmosphere of those planets. Now, at the moment, the best telescopes can just barely see there are planets, and maybe even indirectly. They don't even have images, but very few images with adaptive optics. TMT is not going to just take images of those planets, but also have enough capability to study spectroscopically what are the elements in time, and see if some of them are biomarkers. Okay, so you may be the generation who would say, yeah, we have found a biomarker in an extrasolar planet. Maybe I'll skip through all this. Okay, now last couple of slides. This is when we build these big facilities, it costs money, and governments have to spend taxpayers' money to build these facilities. Why should Indian government support this? Like 1,200 crores. Right? So you make a case. You say, okay, if I look at all the objects in the sky which is changing, variable objects. Many objects in the sky change their brightness. So I plot the time scale over which the change happens versus their brightness. Okay. This is the brightness of the object, this is the time scale over which they change. You plot all the known objects, they are clustered. No changes. They could be very bright object, very faint to very bright, but they are slow changes. We haven't detected anything in this area where changes are happening rapidly. But we know such objects exist. They are not discovered. So just because we don't have the right technology, right telescopes to do that. So you tell the government, see, look, we'll make a telescope which can look in this very fast exposure so that time variability gets low, very high time rates can be observed. It might detect new objects. Right? These are known unknowns. You haven't seen anything there, right? But you know, okay, nature is not so cruel that it doesn't think that. You just have to do the right technology to go and look for it, find new things. So that's known unknown. So you tell the government, look, here is a parameter space. This is an area where you should explore, unexplored territory, new lands, new domains. Okay, exploring. This can be solved, known unknown. But if I take a step back, this is what we used to think our universe looked like, right? For centuries, maybe millennia. There is this Sheshna, turtle, whatever that mountain is called. Yeah, this is all the heavens and hells and all that kind of thing. 7 heavens and 7 hells. All kind of this used to be, we used to believe this is our universe. Right? We used to really believe this is how our universe looked like for millennia. Right? And then we came Copernicus and said, look, no, the sun is in the center, the planets are going around, that's how we do. Very different. Okay? Now, this is our view of it. Okay? I am sitting somewhere in the center. These bright filamentary structures are made of clusters of galaxies or superclusters of galaxies. Galaxies don't exist in isolation. They clump together and form these filamentary structures, which seem to connect together. And there are these big voids where there are no galaxies, that is, we don't see any matter there. I'm sure there's some there, but we don't see any of that. But this is what we think the universe is look like now. Right? This is our view. The best telescope, best facilities have said that this spongy structure hardly fits by anything, mostly empty. Structure is what our universe looks like. Right? That's our world. But then we also know there must be more matter out there. About 96% of what is out there we don't even see. What we saw as filled there is only forming this 4%. We know from other evidences in astronomy that 96% of what is out there we don't even know. We call by various names: dark matter, dark energy, etc. We have no better names. We don't know what it is. Yeah, that is our worldview. So there's a lot to figure out. That's why we built this. It's a very different picture from those millennial old beliefs. But at the moment, our situation is something like this. You're climbing on the elephant. People are saying the universe is made of strings. Yeah. Others are saying the universe is curvature. Others are saying no, it's flat. They're saying fingers of God out there. The universe is unbounded. There are voids in the universe. Depending on which part of the universe you're feeling around, you're getting a different picture. You don't know what it is. You haven't yet put together. 96% of it is unknown. They're still groping out that. Yeah. So the future is astonishing. We are building all these facilities. I told you about TMT. The TMT is just one among many facilities, ground and space-based, which are being built and coming. There's a golden age of astronomy. Golden age of discovery will come in the next 2 decades. We are going to see and address some of the most fundamental questions human beings can ask. How and when did universe come into being? Can you ask anything more fundamental than that? what did galaxies take birth and evolve into what we see today? What is the large-scale structure of this universe? All this filamentary structure. That's the real picture. Is there anything we don't see? What is it made of? What are black holes? How they, is there life anywhere else? All these fancy specificities are going to address. Okay, and it's going to produce enormous amount of data. If we are really good at data crunch, we don't like all that tricks, but we know how to crunch data. Somebody needs to. So, the idea is what is out there in beyond imagination. What we make these specificities are on the basis of those known unknowns. Dark matter, there is some dark matter, you don't know exactly what it is, so you look for it. Dark energy, or that parameter space, that big open area. Don't explore that. See if anything. Those are the known unknowns if you are building facilities. But what you should really pay attention to is what I call the unknown unknowns. We don't even know what they are. You can't even think of they exist. Okay? And those are the ones we are going to change. Well, and so keep your eyes open. These facilities will open up. You will be looking for those known unknowns. That's what your PhD will be made of. That's what you are going to propose as your thesis proposal. Keep your eyes open for those unknown unknowns. They are lurking there to discover. And every time these big facilities are built, the first time Galileo looked up at the sky, he didn't imagine there would be sunspots. Right? Sun was a blemished as God till then. Right? He didn't imagine planets are going on. Right? When the first 1 meter class telescopes were built, and tricky various people looked at the sky, they didn't imagine that the universe is expanding. Right? Einstein didn't imagine that. He put a lambda term in his equations to prevent the universe from expanding. Right? Or from expanding. So they discovered this is unimaginable. So look out for those. Those are the things that are going to change our world. Those are the going to open up new spaces. Thank you. Okay.
So first, I would request Prakash, if any online participants have questions, they can ask.
Yeah, I can.
They would have typed in the chat box. Thank you, Prakash. They connect the table and doesn't look like it. Everybody is ready for snacks. Okay, any questions here? Yeah.
So the objects that you are saying that are being supposed to be observed by this telescope, aren't they haven't the European large telescope tried to observe?
Yeah, so European good question. European large telescope due to the southern hemisphere, first of all. One telescope, 365 days and nights a year, not good enough to cover the sky. Right. They won't even capture the low-hanging fruits, so-called, easy things to capture. There's a lot of that discovered. It's not that the good things are all wiped out in the sky. Just be imagination. Because the other telescope will be in the northern hemisphere. So there's a whole part of the sky, the other telescope only will see. But even otherwise, science-wise, that's your imagination. Like, as I said, sky is not the limit, right? It's just imagination. Any other question?
So the element
it is not strictly root of n, to be honest. It is root of n when you consider light as if they are photons. That's why I said if you collect n photons, looks like photon, because the statistics looks like boson statistics. You can show that. But the true expression is sigma n squared is n into n plus 1. So, if this n is much larger than 1, okay, this average occupancy photon. So, this n is larger than, say, n much greater than 1, then sigma n squared goes like n squared. Which means the error goes like n. Right? But if n is much smaller than 1, n is much smaller than 1, this goes away, and sigma n squared goes like n. Right? So depending on whether light can be treated as waves, where this condition satisfies, then the noise goes like this, which is the case for radio telescopes. If you walk across the road and talk to them, they say, what route that is? It's actually ant. Because no route. Okay. Radio telescopes, but optical telescopes, infrared telescope, visible telescope, etc. This condition satisfies, which means the noise goes like route. And this can be shown because if you look at Planck radiation and this noise statistics, etc., this will come out. Okay. So you didn't need a little bit of time, half an hour to go through it, but I didn't have time. But if you want to come back to this later on.
Okay, but before we take more questions, maybe I just want to confirm that there is no comment. Prakash, is there anyone has raised the hand?
No, none.
So maybe then we will log out from the Zoom and we can continue the discussion locally, but maybe we can switch off our live stream
After that.
Okay.
They want to stay like
yeah. So okay, Prakash, so then we are closing the Zoom link.
Sure, sure.
Okay.